Welcome back, students. So here we are now, we're solving right-angled triangles. And so let's flick through this. Okay, there's a right-angled triangle for sure. We've only one length, but we have an angle. And unfortunately in this example they went and put in two variables. It's all very well, but if you take your length with any one of the variables, we'll take the 12 with the x, then you're going to use cosine, because we know, so basically if you take a variable you want, then that's just as important as a variable you know, like 12, when it comes to figuring out, do I want to use sine, cos, or tan. So the fact that we have the angle here makes it so that when we're looking at 12 and x, we're seeing that the included angle is the reference angle, so we'll use cos for that. But then up here with y and 12, the included angle is the complementary angle, so we would use sine for that one. Or having found x, you'd know two sides, you could go on to use Pythagoras. So here, find the angle. Why are they asking us that? That was from the last section. Okay, so we'll find the angle, no problem. Here we'll use cosine. Here we'll use tan. I hope you can see it. Where does the x meet the 10? It's at the right angle, it's tan. Where does the 10 meet the x? It's at the reference, it's cos. Where does the x meet the 12? By the way, I'll just flick through this, giving you kind of a guideline, then we'll do it again with paper and pen. Where does the x meet the 12? So it'll be sine. I'll do it as quick as I can. Sine, sine, sine. Tan, tan, tan. Okay, I can see what they're doing here. Sine, cos, tan. Well, you'll use inverse cos. You'll use inverse sine. Where does the 9 meet the 15? You'll use inverse sine. Copy, blah, 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 blah. Okay, forget about over here for a second. Let's look here. What are they going to ask us to do? Well, we're going to use cosine. It's going to end up downstairs, so that's no problem. And it's going to end up downstairs when it's the hypotenuse you're trying to get. And remember, cosine is smaller than 1, so dividing by smaller than 1 is making bigger. So it makes sense that the cos is downstairs. If it's the other way around, you're trying to get this from this, it's cos upstairs. Okay, what are we looking at here? Now let's look at pictures, not writing first, because with the pictures we can visualize our learning, understand everything. So what am I looking at? They meet up here in the complementary, in the empty, and the empty means sine. They meet at the reference, it's cos. 18 and x meet at the complementary, it's sine. X meets 8 at the right angle, it's tan. And on from tan then, you've this then. And now what happens is this meets this. Again, it's tan. A meets 12, it's tan. B meets 72, here it's sine. 9 meets C, here it is sine. Use tan for x. Use inverse sine for A. Probably want to get this length using, hang on now, where does this length meet this length? Tan. Where's the question in this? Calculate the length from P to S. From P to S. Okay, so if we're calculating it, we want it, we're interested in it. So where does it, well, hang on, we know angle over here, so we'll have to do some angle chasing. So we'll come over here. Hey, let's do this. Question 12. Yeah, go like that. I went and stapled over my numbers. Well, we'll recognize it when we get to it. Is it? We do it anyway. So, find the values of x and y. Okay, where does x meet 8? Here. So let's write down the tan of 62 degrees equals tan of 62 equals x over 8. Bring up the 8. 8 tan 62 degrees. Clear 8 tan 62 is equal to 15.04. And we could round it, but a nice trick to so that we don't have any compounded errors is to store it to a. We could even store it to x because it is x. Okay. Now we know it. Let's just say about 15, but we'll have the exact value in our calculator. And now what are we doing? We're seeing where does the 15 meet the y? It's another tan. So we'll say that the tan of 37 degrees equals x, which I know, over y, which I don't know. The y comes up, the tan goes down. And we'll plug it into our calculator. Clear x upstairs, bring it up, bring it back, fraction, tan downstairs. I think I might need to close that. If I don't, I think I'll get an error. So here you saw it. Okay, so we go again. Just wanted to show you that. I knew it was going to happen, kind of. So because I've seen it before. So tan of x over tan of 37. So you don't normally have to close out the function argument bracket, but you do here. So it's the tan of 37, and we'll close the bracket. Okay, it equals, shift equals maybe. Let's just go straight equals because it won't make any difference. 19.96. So we're not going messing around with our rounding for the whole rest of our lives because it's destroying our learning. We'll just do that in the exams. So we've y in question. Well, I don't know where I am now. It's 20 rounded, yeah, and it was 15 rounded. But it's important to know they're not rounded. It's giving a slightly false impression. So we do this one. I think this is equally easy. It's tan 60. By the way, we know what tan 60 is. It's root 3. So it's root 3 equals x over 8. We know that tan 60 because when you're 30, 60, 90, you're 30, 60, 90, you have 1 is to 2 is to root 3. So when you take the tan of 60, you get root 3. And when you take the tan of 30, you get 1 over root 3. So we might as well know them and apply them. So I'm okay here. So I have 8 root 3 for x. So let's just leave it like that because that's it exactly. Definitely won't reduce. So I have 8 root 3 for x. And now I'm going to try and get a, but I have to see where x meets 20. It's the complement. So I'll say that the sine of a equals 8 root 3 over 20, and we'll inverse sine that. Okay, and oh, sorry, I can't off screen there. Bring that over here too, and we'll inverse sine this, and we'll get shift inverse sine. Try it now. 8 root 3. Will it let me go downstairs then, or should I get out first? See, can we get all the way downstairs? We can. All over 20. Okay, come out and close your bracket. Close your roundy bracket. and we get 43.8. I'm not messing with the rounding. We'll look at it there. Is there something around 44 degrees? Fine. It's a rectangle with 11 going this way, and they're going to give me this person doesn't know how. Well, find the length of diagonal DB. Did they ever hear of this? It's just a bit annoying that they don't say find the distance from D to B. Okay, so we've got it from distance from D to B, and where does it meet 11? It meets it here, so it's cos. Cos of 28 degrees equals cos of 28 degrees equals 11 over what we're looking for. Bring what we're looking for up and bring the cosine function down and plug it in. I wish I knew what number question was in question 11, and it comes out to be 12.5. Okay, this is the one we decided we'd go for. Okay, I have it here. Diagram rests frame for roof. PQ is 7.5. You can see that. So this is your split attention. This is when it's not nice what they're doing to you now when you're reading this, because so basically, let me come up with a guideline here. You have to separate the situation from the questions. Okay, and if the situation gives you a lovely picture, try to assume that the exact same data is just being repeated here. Now, if you need something, and I've never seen it happen, but if you need something, you can come in here and look for it. So basically what I'm saying is we cross all of that out and save ourselves the cognitive load, the mental load of reading it, because that'll make our life easy and we'll be better at maths. Okay, so calculate the length from P to S. So by writing it in here like this, instead of introducing a variable, we're not going away from the notation of the question, number one, and number two, we are we're starting our problem solving process and our visual process. Now they both meet at a right angle. Oh, and hold on, I can't. So you're going tan, but there is no angle, and of course then you're going, hold on, it's Pythagoras. Okay, so if it's Pythagoras, we're going to go and see. Sure, we're getting a hypotenuse, so it's the plus version. So we'll go to our calculator and go to square root of 7.5 to be squared plus 3.2 to be squared. Okay, and that's this 8.15. You see, I really annoyed that they wouldn't write PS equals, because then it just it'd be much nicer if they had written PS equals 8.2. It's nicer to do statements. Find the angle at R. Let's double check from S to R to Q. Find this angle here. Okay. Again, just like we write this, we could introduce a variable, but I kind of need to start not being afraid of these things. But maybe I need to start interacting with them, S, R, Q, and using them more often, so I gain my confidence. But another guideline is the one in the middle is probably where you're at, if there aren't several angles joined together. Okay. So what we're going to do is well, that's actually completely separate to this. So we're going to tan it, aren't we? So we're going to inverse tan 3.2 over 4. Or we're going to inverse tan, if we don't want to have a decimal place, just press the decimal button, 32 over 40. Same thing. Shift inverse tan, fraction bar, 32 over 40. 38.6 degrees is my angle, and that's question 12, rounded up to 39 grand. there's so much space there, isn't there? Okay. So, remember what I said. Let's just go straight to the diagram and straight to the question. 1. CD, correct to one decimal place. Get length CD, this to this. Okay, so let's write it on our diagram, because that means we want it. Where does it meet? What's the included angle between that and something we know? It's a right angle. So it's tan of 35 degrees equals distance CD over 6. CD is already on the top. We just want to take the 6 out from under it, so it's divide by 6 here, we multiply by 6. Plug it. I just read it off the answer sheet. It turns out to be 4.2. Okay, when rounded, that comes out to be 4.2. And plug that into your calculator by all means. Now this, it's not proof. It's a bit lazy. They should have said cos squared 45. It's bad that they didn't use the argument brackets here. We're getting. I already explained to you that this is a bit sloppy. That it should be this, and certainly if you want to square it. But what does this mean? It means cos of 45 all to be squared. If we want to be more specific about it. So, and in the calculator, you're not going to have this. You're never going to be able to make it. What you are going to be able to make is cos of 45. Now we also know, or you will know, that cos of 45 is 1 over root 2. So when you square it, you get 1 over 2, because square the top, square the bottom. Okay, go on to this one. Like I said, it's 1 over root 3, because we just know that, and I'll have to give you a separate video on this, but or will I do it right now? Let's do it right now. Give me some paper. And I'm going to open up in front of us for a minute the log tables. Do I need to? I don't really need to. I need these two triangles. That and that. And I will just open, yeah, I will open log tables here to show you that they are important and they're in the tables. Hopefully this is my, yeah, here we are. So what I want to go to would be trigonometry. Might be back a bit. So there's stuff going on here, but it's kind of summarizing. Okay, we'll bring it right down to fundamentals. Yeah, that's the lazy way in geometry, but you're allowed to do it, of creating a right angle. Working line, find any reference point, mark a reference point. So I'm going to go with 1, 2, 3, just to check. Can I open this wide? I can just about. Okay. Now what I want to do is create a triangle like this with 2 here and 1 here. That has a right angle. How will I do it? Okay, so let's start off by saying, come on up. Oh, I've opened this again. That's okay. I can calibrate my compass to any of these. So let's calibrate it to 1 and put that in there. Let's calibrate it to 2, or open it to 2 ticks, and put that from there up there. Okay, now let's join them. So we have this 1 is to 2, This is a construction, by the way, a triangular construction, so we've done one of the constructions in your course. So we've 1 is to 2. Now with Pythagoras, you can go the square root of 2 squared minus 1 squared for here. So now we know this is root 3. And with our calculator, or with our, indeed by fitting it with this, you will see that it fits perfectly. Or of course you can take a protractor and you can measure the angles, and we will see that it's 60 degrees here, 60, and it's 30 degrees of course up there, the complementary angle. Okay, over here like this. Okay, we'll keep going because I have to. So you missed seeing all of this. So what I did there was I opened up a working line and I defined with my compass 1, 2, 3. Okay, I made a right angle just straight forward with another working line and with my right angle. I used a 1 here by opening this out 1 and making a tick. I opened it out 2 and went there. Now I have 1 and 2. I used Pythagoras to say that that's root 3. Now then I measured it and I found this to be 60. Now that's only roughly, it is 60 exactly, but we can only say it's roughly by measuring. But what we could do then is we could bring in we know there's 1 here and 2 here, okay, and they meet. So we have 2 and 1 meeting at an angle, so we can use an inverse cos on that. So I could do a shift cos to check, well, is it exactly 60 or is it roughly 60? So the inverse cos, well, 1 over 2 is 0.5. And that's exactly 60 degrees. Okay. Now by the same token, I'm going to generate, let me just put a right angle up here, and I'm going to generate an isosceles right triangle. I'm going to generate an isosceles right triangle. And in this it's even easier. You're just going to take 2 measurements the same. It doesn't matter what they are. I'll call, just for accuracy purpose, I'll use a longer one. I'll call that my 1 now, or my side and my side. So they're the 2 legs of a right triangle. So you can join this to this. We can use Pythagoras to show that 1 squared plus 1 squared equals root 2. Okay, so now I have root 2, 1 and 1. I can do inverse sine or inverse cos. So say I want this angle, it's 1, or this angle. Well, they're the same, right? Because you have 1 and 1. So you have by definition you have an isosceles triangle. So it doesn't matter which I do. So let me come in here. Well, let's start again. Shift, sine or cos, whichever one's near to me, that'll do. Okay, 1 over root 2 over root 2, and that'll be 45 degrees, okay? And therefore that generates a good bit of stuff. And why did all of this arise? Because, oh yeah, we got to this. So now we know the cos. So basically, and you can always go, if you have 45 degrees, okay, you can kind of go, look, that's equal to that. 1 root 2. This is 45 degrees. So the cos of 45 degrees, and it becomes very, very famous. Okay, the other thing is your cos is falling, your sine is rising at 45 degrees. They're both the same. They're equal to it. It evaluates to you know, a quick way to get 1 over root 2 in your calculator is just to do sine 45. Now that is root 1 over root 2. Even if I put in 1 over root 2, it's going to say that, because they're doing a thing called rationalizing the denominator, which means they're multiplying the top and the bottom by root 2. So if I multiply the top and the bottom by root 2, I'll get root 2 over 2, which is what it says here. Okay. And then, so these two are the same. And if I want to get the cos of 45, I am getting 1 over root 2. So I know the cos of 45 is 1 over root 2. And this is squaring it. Now, of course, like I said, we can always, so if I'm, sorry, I keep changing my train of thought, but if I'm squaring that, I'm getting squaring the top, 1 squared, squaring the bottom, root 2 to be squared. But your 1 squared is 1, and root 2 to be squared, a root and a square cancel each other out, and you have 2. Okay? Of course, but now you could just go bog standard, let's write the cos properly of 45. Let's close and square, and yeah, you get that, but you're not really learning anything then. Now I'd also back there in this diagram done this guy, putting 1 and 2 by construction and using Pythagoras for root 3. We know from this that 60 degrees, I proved that it is using an inverse sine cos tan, doesn't matter which, and so I proved it's 60 degrees here, and so it's 30 degrees up here. So let's ask the question, what's the tan of 30? Well, let's go through it here. 1 over root 3. So if 1 over root 3 is the tan of 30, if I square the top and square the bottom, I'll get a third. And we can just do that here too. Open. Do I need it? Hang on, let's see, do I need it? Do I need, they're called nested brackets. Do I need the second nested bracket? Let's see how I go with tan. The tan of 30. Now, if I square that, or am I squaring the tan of 30, or am I, well, we'll know by seeing our answer. So it's not squaring the argument, so that did work. Didn't have to put the outside brackets. Great. Okay, I learned something there. I hope you did. On to sine squared 60. Well, what you want to do is draw this. Now remember, 60 degrees makes a taller triangle. You've got 1 as the shortest leg, you've got 2 as the hypotenuse, and you've got root 3 as the longer leg opposite to 60 degrees. So you work your way through this and you go, hey, the sine of 60, forget the square for a second, the sine of 60 is root 3 over 2. So this is root 3 over 2 all to be squared, and this is the way you should be doing it, because if you're doing it this way, you're really doing the learning you're supposed to be doing. Now root 3 squared is just 3, and 2 squared is just 4, and that's the answer our calculator is going to give us. Let's have a look. So clear the decks, and now we found now we can, where was I here? We found now we don't have to have what I was going to call the outside bracket, but we can't put a square there. We have to go sine 60, close your bracket, and that's going to happen first, and then you're going to square the answer. So the priority of operation is sine comes first, then square. It's funny that, because sine then is, because when we were doing priority we didn't have sine cos tan to be thinking about. We get 3/4, and then you have that there as well. I forgot to say that. Well, I did say it, but we're also saying it's the sine of a to be squared. Much better. Okay, this is getting a bit involved now. Show that 1 minus sine squared equals cos squared. Well, you can just go to that identity that you have here and say cos squared plus sine squared is always equal to 1. Oh, okay, and that would be a way. But what they want us to do is, they want us to say, well, I know that the sine of 30 is a half, and we did it in the previous page. So when you, so this is a quarter. Okay. I'll write it out more fully. It's 1 minus, when you do the sine of 30 here, we'll look at it here, in case you doubt me. And you should, until you get to know it. Well, how do I know it? Well, I went back to this reference triangle. So, by the way, the whole triangle is called a reference triangle too. So if I want 30 degrees, I'll put a 30 degrees there. And I'll go, okay, 1 is opposite me, 2 is here, root 3 is here. So you can go from your 30 to this reference triangle. Then you can say, but hang on a second now, what's the sine of 30? The sine of 30 is opposite over hypotenuse, so it's a half. And when you square your half, you get the quarter that I talked about. And then you can go, that is 3/4. Now the other one, cos squared 30, well, we have our 30 here too, so it's root 3 over 2. So you see your root 3 over 2 to be squared equals 3 over 4. That escapes the square root and the 2 gets squared, and you have 3/4 equals 3/4. Okay, and that's your finish of your proof. It doesn't only happen for 30 degrees though, it's an identity. Okay, because sine squared plus cos squared is always equal to 1. On we go. Let's do it this way. So what is the sine of 60? Well, there's 60 degrees here. The sine of 60 is root 3 over 2, just like it's the same as the cos of 30. Why is that? Because your sine is going up, your cos is going down. The sine of 30, you can see the way it's going up steeper at the beginning. So even though you're only out a third of the way, you're up half the way. The sine of 30 is a half. 45, by the time you get to 45, you're up 0.707, which is 1 over root 2. And by the time you get to 60, you're up root 3 over 2, which is what we saw there. Okay, so the sine of 60 is root 3 over 2. You can do it both from the graph or from here. The sine of 60 is root 3 over 2. And they're asking you to look at what is, so let's do the squiggle, because we're not sure yet. So root 3 over 2, and I've squiggled 2. Hey, what's the sine of 30? Sine of 30 is 1 over root 3. And the cos of 30 is root 3 over 2. Okay, they're all multiplied together. Where's my 2 gone? 2, yeah, this is all multiplied together. You've you have the root 3's cancelling. You know, so quiet I got when I started having to work. And one of my worries is, should I be talking so much during the videos, or should I be doing them in silence? And then you think, but you can always turn me down, turn the volume off. Sine of 60 is root 3 over 2. I'm going to have a picture there when I'm pointing up at it. So sine of 60 is root 3 over 2. We'll do a squiggle until we're sure, until we see what happens. You have 2 times sine of 30, and you're going to keep going back to your reference. We'll make a long one this time. So with 30 here and 60 here and a right angle here. This is the 1, this is the 2, and this is the root 3. Okay. Sine of 60, root 3 over 2. 2 is just a 2 because it's sitting there, we're asked to check it. We just see are these the same, squiggle there. Now I'm on to sine of 30. The sine of 30 is 1 over 2. And now I'm on to cos of 30, which is root 3 over 2. Okay, one of those 2's cancel. You're left with root 3 over 2 is no longer squiggle, equals root 3 over 2. Done. Okay. Whew. That's a tough one. So we're going to question 16. Now, can we get away without reading? Maybe. Find the area. So it's a classic. I've done this loads of times. It's a classic because what you have here, guys, is you've 20 and 40. So that's 1:2. So, and of course you also could have known you'd 60 degrees here because it's an isosceles triangle. So this is the angular bisector. So this is 30. So you have the 1. 1:2 is to root 3. and then by ratio, by proportion, so this is 20 times bigger than root 3. Okay, so we've can you see my pen? Let's use pencil. You've 20 root 3 pacing upwards. You've 20 out. Now that's a right angle, so we can get the area of that real quick. Half the base is 10 by the perpendicular height. So that's, and by the way, the thing appears twice, so instead of going half base by height, we'll just scratch that because we've doubled it. So we'll do base by height. That can't be right. We will do this base. Okay, come back. Sorry. Let's do the full triangle. Half the base is 20. The height is 20 root 3. 20 by 20 is 400. So we get 400 root 3. Are we on 22.4, question 16? Area is 400 root 3. Based on the symmetry of the triangle, describe a second method for calculating the perpendicular height. Maybe what I did was, okay, oh yeah, so you could use inverse. You could put 20 here, right angle here, and 40 here, and do the inverse. So where do they meet? They meet at the reference angle, so it's cos. What am I trying to find? Describe a second method to calculate this. Yeah, well then you could use that, and that, and this. So you could use, using the 60, you could have used sine. So enough done. Okay, I hope 16 was the end of it. So that's section 22.4 done. There's some tricky stuff in there. And that's your problem solving. I'll move on to 20.5 next. Okay. See you in the next one. Okay, keep learning, keep working hard. You're doing great. See you next one.